All right. Okay, let's just review a little bit about the consequences of zero correlation. Okay, there's at least the 3 consequences. The first one is the OLS estimators are still unbiased and consistent. The second one is the OLS estimator is no longer efficient, and means that there are no longer blue best linear unbiased estimator. Okay, and the third one is the in most of cases, OLS standard errors are biased. Then which means the estimated t-value and f values is not reliable. Therefore, the hypothesis testing is unreliable. Okay, then I think we will see all these consequences using the real examples. And I'd like to explain a little bit about this, the second points. Okay, we say that the serially correlated error terms, the OLS estimator in the serial correlated error term is actually this serial correlations error terms causes the dependent variable to fluctuate in a way that OLS estimation procedure sometimes attributes to the independent variables. Let's say it again, okay? I mean, the error terms, if we do have serial correlations, is because of the dependent variables is also fluctuate in a serial correlated way. But the OLS estimation procedure, okay, the OLS estimation procedure sometimes attributes this variation to the independent variables. So OLS is more likely misestimate the true beta in the face of serial correlation. On balance, the beta are still unbiased because overestimates are just as likely as underestimates. But these errors increase the variance of the distribution of estimates. Increasing the amount of any given estimates is likely to differ from the true beta. Means that the serial correlation problems cause the OLS to misestimate the true beta, either overestimated or underestimated. And actually, on balance, I mean, the expected value of the beta hat is still the true beta, but their fluctuation is caused by serial correlation. Is that clear? I know it's a little bit harder to understand those serial correlation behind. Any questions? Any questions? Well, maybe you can go back home then and read some more about the textbook. If you have any questions about this, and you may ask next time, okay? All right. So after we know the consequences of serial correlations, and I like to go on to the section 9.4, which is the detection of serial correlation. All right, then how can we detect serial correlation? Most of the econometricians rely on formal tests. And we're going to introduce two formal tests. One is called Durbin-Watson test. The other one is called Lagrange multiplier test. Okay? And the Durbin-Watson test. So first, let me introduce Durbin-Watson test. Okay, Durbin-Watson test is used to determine if there is first order serial correlations. Remember, only first order serial correlation. Durbin-Watson test is used to determine if there is first order serial correlations. Okay, again, I like to mention that the form of the serial correlation is not only first order, but we have another form of serial correlation, like second order, like season order serial correlation. But remember, Durbin-Watson test is used only first order serial correlations. Okay? And it is also important to know that the Durbin-Watson test, only if we want to use the Durbin-Watson test, only when three assumptions are met. Okay, what are they? These three assumptions. First one, regression model includes an intercept terms. The first one. Okay, the regression model includes an intercept terms. I don't think we have any problem of this one. Usually we do the regression model always includes an intercept term. The second one, the serial correlation is first order in nature. Okay, the serial correlation is first order in nature. The third assumption is the regression model does not include a lagged dependent variable as an independent variable. Okay, in other words, we have the, when we say independent variables, okay, the notation we're using X, okay, which means, this is just by theory, it is just a factor. It's possible factor to affect the variable Y. But sometimes we do have the model with lagged dependent variable as an independent variable. When we say lagged, means like Y with T minus 1 as a subscript. Okay, so usually we have Y in the Y variables, which the time periods notated as T. But we have another Y minus T as an independent variables, which we call it lagged dependent variable as in independent variable. So if you have the regression model with lagged independent variables and independent variables, you are not able to use Durbin-Watson test. Okay, so these three assumptions is important to remember when you use Durbin-Watson test. Okay, then how do we do the Durbin-Watson test? Remember, when we do the hypothesis test, we need to calculate the statistics, right? So usually the regression model, in regression model, when you do the hypothesis test, the t-value is what we call test statistic. Okay, so now if we want to do the Durbin-Watson test, okay, we need to know what is Durbin-Watson test statistic. Okay, it's like the equation 9.10. Okay, look at this notation carefully. Okay, all right. Usually when we do, excuse me, we know that most of the applications follows positive zero correlation. So if we use Durbin-Watson test to test for positive zero correlation, we need to follow some steps. Okay, and you can refer to our textbook on page 304. Okay, so the first of all is obtain the OLS residuals from the equation. Okay, then calculate the D statistics by using equation 9.10. Okay, let's see this 9.10, this D. So we're talking about this D. So what is D? D is after you do the regression analysis using OLS, then you will have the residual terms, right? Which is denoted as ET. And this formulas tell us that using ET minus ET minus 1, okay, square it and add all of the observations from, this is started from 2, right? Why? Why it is started from 2? Because there's a t minus 1. Okay, so we have all the observation from 1 to capital D, T. And since the calculation is using ET minus ET minus 1, so we started from second, means using the second residual minus the first residual, square it, and add the second one is using E3 minus E2 and squared it up to capital T, all the observations. So this is the numerator. And denominator is the square of the residual, the sum of all the square residual. Therefore, the summation here for the denominator is from 1 to T. Okay, so first of all, you need to obtain this OL as residuals from the original equation and calculate the D. The second step, okay, look at the page, page 304, okay? Determine the sample size and number of explanatory variables. And then, so in our exam, we need to determine the sample size and the number of explanatory variables. Then consult the table B4. So would you please turn to our appendix? Okay, let's go to the table B4. Okay, this, I don't have this in my PowerPoint, okay? I don't have this table in my PowerPoint. So would you please just look at the textbook, which is on page 543. This is called Critical Values of the Durbin-Watson Test Statistics. Okay, and if you look at the table, this table is arranged. The first column is N. N means the number of observations. And starting from the second column is the number of explanatory variables. Okay, so it's denoted by k equal to 1, 2, up to k equal to 7 in our textbook. Okay, in each k, I mean in each number of explanatory variables, they do have upper limit and the lower limit. I mean the critical value, upper critical value and lower critical value. Okay, so I'm going to use the example to do this one, okay? And so let me see. Let me see if there's any other things. Okay, let me go to you. I'm using one of the examples which from our textbook, chapter 9. Okay, and the data set is Chick 9. Okay, in our textbook, they're using this example too. Okay, so let me show you. I already downloaded the eViews, and I'll show this Gretel too. Okay, this is this is the data set Chick 9 with with y variable y. Okay, y variable as a the explanation. I mean the data variable explanation is on our textbook 306. Y is per capita chicken consumption in pounds in year T. And the 3 X variables for PC is the price of chicken. Price of chicken in cents per pound in year T. And PB is the price of beef in cents per pound in year T. And the third variable, independent variable, YG, is US per capita disposal income in hundreds of dollars in year T. Okay, so this is the data from 1972 up to 20,002, 2002, okay, which we have 29 observations. So let me show you how to do this Durbin-Watson test. Okay, first of all, let's run the regression. So y, using y, using y as an y variables in PC, PB, and YD. Okay, then we open as an equation. So run the regression. I already did it. Okay, so if you do it, my equation is already here. Okay, let me make it bigger. Is it okay to make it bigger? No, there's no way to do it. Okay. Then let's see this output. According to the residual, according to the Durbin-Watson test, okay, we need to obtain, after we do this estimation, we need to obtain the residuals. And we need to calculate the D statistics. But there's a good news is that you don't have to do it by yourself. In our output from eViews, did you see this Durbin-Watson statistics? Did you see this one? It's already here. So these formulas I show you, this one, after we do the regressions, then using this 9.10, and you will get the Durbin-Watson statistics. In our example is 0.99299. Okay? All right. After you have Durbin-Watson statistics, okay, then we need to find out the number of the sample. We need to determine the sample size and the number of independent variables. So how many sample size do we have? 29. How many independent variables do we have? 3. Okay, so let's go back. So would you please all do that, okay, with me, okay? Then you will know how to do it. So check with the sample size N. Now we have 29. And what's the K here? We have 3. So did you see the DL and DU? What are they? Anybody answer me? What did you see? With sample size 29 and K equal to 3, we do have lower critical value and upper critical value. Anybody like to answer me? You all follow me? Check with the textbook.
The upper one is 1.62, right? And the lower one is 1.22.
1.65. The other one is 1.20. Upper one is 1.65. According to my book.
Yes, it is.
Then lower limit is 1.20.
Yes.
Okay, then what's the Durbin-Watson statistic we have? 0.99299, right?
Yeah.
Right.
Okay, which is lower than the lower limit, 1.20. Okay, all right. So how do we decide? How do we decide? Well, let me go back to my uh, PowerPoint again. Okay, I like to explain more about this Durbin-Watson statistic. Okay, look at this D. Okay, when we calculate our examples, the D is equal to 0.99 something. Okay, look at these formulas. If there exist positive zero correlations, okay, and if they're really positive, means that, well, remember the range of the row. Remember that? The range of the row, excuse me. I'm sorry, where is it? Okay, it's between -1 and +1. So if you're really, really positive zero, I mean, very close, extreme positive zero correlations, means ET and ET -1 is pretty close, right? So the difference between ET minus ET -1 is very small. And you square it, it's even smaller. Then add all these small things together, our denominator is pretty small, right? So here, did you see that? For extreme positive zero correlation, D will equal to 0, means that D is close to 0. So if you have the D statistics, which is small, the small number means it's close to 0, then it is really show the positive zero correlations. All right. And the other extreme positive negative zero correlation situation. When we say negative correlation, means T and T -1 is really opposite signs. One positive, the other one be negative, positive, negative. Okay, so for extreme case, for negative, this ET minus ET -1, they're really opposite. Okay, so one is positive, the other one will be negative. And for extreme case, this will becomes to 2 double ET. And when I do the double ET square, it becomes to 4 ET squared. And we have the summation, all of them summation. So the D becomes to close to 4. Okay, so if you have the Durbin-Watson statistics, which is extremely negative correlation, you'll know that your D numbers is pretty close to 4. All right. Then if you don't have zero correlations, the D will close to 2. How is it? No zero correlation means these two are really unrelated. Okay, then mathematically, no, we'll end up with D close to 2, which is in the middle of 0 and 4. Okay, all right, and then we understand the meaning of the Durbin-Watson test. Okay, so in our examples, in other words, after we do this OLS estimations, if you look at Durbin-Watson statistic, which is close to 2, means there is no zero correlation problems in this model, regression model. Okay, if this one is pretty big in terms of the number of 4, close to 4, means negative zero correlations. If it close to 0, means positive zero correlations. Does that make sense? But, you just have this close to 4 or close to 0. You cannot do the formal hypothesis testing. We need to have critical value, upper critical value, and lower critical value. This is where these tables, upper critical value and lower critical value coming from. So in our example, using k equal to 3 and the number of observations is 29, we do have lower limits and upper limits. Upper limits is 1.65. The lower limits is 1.20. But how do I make the decision about this lower limit and upper limits? Okay, would you please go back to our textbook? Okay, which is page 304. Actually, the Durbin-Watson statistics is working with the hypothesis testing, which show on the 9.12. You all see that? Let me see whether I have this one. Okay. So we are working with the null hypothesis of positive zero correlation equation 9.12. In other words, the null hypothesis, so the purpose is checking with the positive zero correlation. So the alternative hypothesis is rho greater than 0, means positive zero correlation. Okay, and null hypothesis is less than or equal to 0, means no positive zero correlation. And what's the decision rule? Okay, the decision rule is like this. If D less than DL, means reject the null hypothesis. D less than DL. Okay, remember the DL. What's our DL? The lower limit in our case is 1.20. Okay, then our D is 0.99, right? I just showed that 0.99, 299. Okay, and the DL for our case is 1.20. So D really less than 1.20. So we will reject the null hypothesis. So if you have your D greater than upper limits, then you do not reject the null hypothesis. However, if you have the D falls between lower limits and upper limits, means inconclusive. Okay, before when we do the hypothesis testing, we either come up with the reject the null hypothesis or do not reject the null hypothesis. We don't have anything which is called inconclusive. But remember, Durbin-Watson test do have the situation with inconclusive result. Okay, all right. So in our examples, we have the Durbin-Watson statistics 0.99299. Then this is called reject the null hypothesis. Means that the regression model, this regression model do have serial correlation problems. Okay, any questions for this test? Do I make it clear?
Professor, I have a quite confusing one. At page 303, and there is no serial correlation because the D is close to 2. I think
Yes.
before we said the 0.99 is close to 2, right? It means no serial correlation.
0.99 is not close to 2, it's close to 0.
It's close to 0. All right. Okay. Okay, I got it. Thank you.
You know, when we say D equal to 0 is a positive zero correlation. If D equal to close to 4 is negative zero correlation. And in the middle is equal to 2, right? So 2 means no zero correlation. But now the number for 0.99 is close to the 0. There's close to 0 side instead of close to 2 value of 2, right?
Okay, yes.
Yeah, okay. Thank you. Thank you for asking the questions.
Thank you,
Any other
Professor.
questions? Any other questions? And I also like to mention that Durbin-Watson test is one-sided test. Okay, this is one-sided test. Remember, Durbin-Watson test is used to test for one-sided test for positive zero correlations. In our textbook, if you check with page 304, okay, and this is also mentioned about the steps to do this Durbin-Watson test. And the third points, okay, the third points which shows the hypothesis testing, 912, okay, but in the middle parts, there's another the other 9.13, okay, and in our textbook shows that in rare cases, a two-sided Durbin-Watson might be used. In rare cases, okay, then hypothesis testing, since this is two-sided, so becomes to null hypothesis rho equal to 0, and alternative is rho not equal to 0. Okay, and in this case, the decision rule will be different. Okay, although you know, for reject the null hypothesis, there's two situations we reject the null hypothesis, since there's a positive and negative, right? So if D less than DL, okay, according to what we have here, D less than DL is reject null hypothesis. Okay, so for two-sided, D less than DL, again, this is reject null hypothesis because of the positive zero correlation. But if you have the D greater than 4 minus DU, you still can reject the null hypothesis because this is negative zero correlation. Okay, this is more, it's a little bit complicated. I mean, the decision rule. But if you follow this decision rule, if your D is greater than 4 minus DU, okay, DU is the upper critical value, okay? And if D is between this area, okay, 4 minus DU and 4, I think this is wrong. The PowerPoint here, this is only DU, no 4 point. I have to erase this one. This is wrong. Okay. I'm sorry. Okay. All right, I need to do this one. Okay. All right. And there's also otherwise is inclusive. Okay. You don't have to really remember this decision rule when we go to the Durbin-Watson test, and we can just follow this rule to check whether we'll reject or not reject. Okay, and I think the easiest way always is to check the Durbin-Watson statistic was number 2, because 2, if it's close to 2, definitely there's no zero correlation problem. If pretty small or pretty big, small means positive zero correlation. Really big is negative zero correlation. Okay, but excuse me. Any questions so far? Any questions? Okay.
Sorry,
Yes.
Professor. So we don't need to really check for the formula here. I will just confirm the result of a Durbin-Watson test from the regression, right? If it is close to 0, that's positive zero correlation. If it is close to 2, that's no zero correlation. If it's bigger than 2, maybe it is possible for negative zero correlation.
Yeah, this is very rough. And then of course you need to follow those rules. You need to follow the rules. Something like this one. If you're using the Durbin-Watson test, and check with the table. But roughly you can see whether you can see whether you do have possible zero correlation problems. But don't worry about it. There's another way to do it, which is even clear. Okay, I'm going to show you another one. Okay, this is one way to do it, Durbin-Watson test. The other one is called Lagrange multiplier test. Okay. Oh, it's almost about the time. Okay. For Lagrange multiplier test, I can show you a very quick way. And maybe you can go back home and review this Lagrange multiplier test before next class. Okay. Let me show you very quick, in real quick way. Okay. So after you have this output, okay, hit the view and residual diagnostic, then choose serial correlation, LM test. This is what we call Lagrange multiplier test. Okay, hit it. Again, legs to include. Okay, I'm just showing you very quick, which so far we use one. Okay, then let me explain it later, next time, why I choose one. Okay, and hit OK. Then, what did you see? How come I didn't? How come I cannot get rid of this one? How do I get rid of this one? Uh-oh. Uh-oh. I'm sorry, where I am. Where I am. Well, okay, this one, okay? And look at this one. Observation times R squared. And I do have these numbers, which is a chi-square distribution with degrees of freedom. And this is the p-value. Okay? In these examples, it shows that we do have serial correlation problem exists. Okay, I think I will explain this one next time. Okay, let me show the Durbin-Watson statistics using the Gradle. Okay, model. I'm doing ordinary least square. I have y as my dependent variables, PC, PB, and YD as my regresses. Okay, and I hit OK. After I have this one, then I'm hitting the test. And did you see this Durbin-Watson p-value? Durbin-Watson p-value, okay? And here it is the result. Do we have just 99.29, right? 0.99299 Durbin-Watson statistics. And if you test the positive autocorrelation, the p-value shows that small. Did you see that? 0.000196663. And if you check with the negative autocorrelations, which p-value is like this one. So since we're checking with the positive autocorrelation, so with this p-value such small, so we reject the null hypothesis, means we do have positive serial correlations. So from Gradles, you really can see the p-values, but from eViews, you need to check with the numbers. Let me see. Oh, let me go back to where is my? Well, where is it? Okay, this one. This is from Gradles. I do have this p-value shows, but in eViews, you just have to check with the tables. Okay? This is for today's. Is it okay for today's?
Yes, thank you.
Is it clear for today's lecture?
Yes, very
bro.
clear. Thank you.
Very good. Thank you, bro.
Okay.
Thank you, bro.
If you have any questions, just go back to the recording, or maybe if it is possible to be in the class next week, we can come to the class and ask. Okay, let's just wait and see the situation. Okay.
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 Right. Okay. That's
Bye-bye.
Bye-bye. Bye-bye.
Bye bye. Thank you, bro.
Thank you.
Bro.
Thank you. Thank you. Thank you. Bye-bye.